Everyone. In this video, we're going to begin section 14.6 on the chain rule. So you've seen the chain rule before in single variable calculus. So let's just recall the chain rule comes in when we have a composition of two functions, say f of g of x. And what that rule tells us is if we want the derivative with respect to x of this function, then what we have to do is first compute the derivative of f with respect to g, and then compute the derivative of g with respect to x. Oftentimes, this g of x is denoted with a u, so that chain rule formula looks like df du, du dx. Okay, so just kind of the takeaway, chain rule is a procedure or a way to take the derivative of a function that is a composition of a function, of two functions rather. Okay, so similarly, in multivariable calculus, say if we have a function of two variables, we'll meet a function here in a moment, f of x, y, and x and y are themselves functions of another variable, say t, then we need a special rule for computing the derivative of such a function. All right, so let's go ahead and get started. So let's take a look at this preliminary example. It states let t equal the function f of xy and let it represent temperature at a point xy in the plane. And we've seen this type of function before, or this type of context. And let x equal g of t and y equal h of t represent x and y coordinates of the particle in meters after t seconds. So notice that the inputs for our function f are in fact functions themselves, functions of time. Okay, assuming that f, g, and h are all differentiable, derive a formula for the derivative of t, temperature, with respect to little t. So just to summarize the functions and the players that we have here, we have our function t. So this is the function of temperature, but it's a function of x and y. But then we have two other functions, x and y. And these are both functions of time, or t. So then we've seen the computational formula for the derivative or differential looks like the following. Derivative of t equals the partial of t with respect to x dx plus the partial of t with respect to y dy. So this is just the computational formula. And we have met this formula in a previous section. This is just the differential. Okay, but now we're wanting to compute the derivative with respect to t, little t, time, of the temperature. So for that, the formula looks slightly different. So here, derivative of t with respect to time is going to be the partial of t with respect to x times the derivative of x with respect to t. Notice that here, x is a single variable function. X just has one input. So the derivative that we're computing is just a regular derivative, dx dt. So then we add that to the partial of t with respect to y times the derivative of y with respect to t. Cool. So there would be how we'd compute that derivative of our temperature function with respect to time. So a couple things that I want to address here, first of all, are units. So if we go back, we see that temperature, T, is not given any units. So let's just call it, say, degrees Fahrenheit. Little t is in seconds. So if we look at what our units are here, we can just look term by term. So first, partial of t with respect to x, so that would be degrees Fahrenheit with respect to meters, because notice here, we are told that X and Y represent the coordinates of the particle in meters. So then dx dt would be the change in meters, so meters over the change in time, so seconds. So notice here, the meters cancel. So we're just left with degrees Fahrenheit per second. And then in the next terms, we have again degrees Fahrenheit per meter, because partial with respect to y is meters, or y is, the unit of y is meters. And then dy dt would just be meters over seconds. So again, meters cancel. So we see here that the derivative will have units of degrees Fahrenheit per second. So sometimes such functions get a little more complicated. So for example, suppose we have a function that is a composition, but the functions themselves are compositions too. So kind of a triple iteration here. So like f of x of u of t, for example, and then we just have, say, y of t. So we can have some funky or interesting behavior going on when we have derivatives of multivariables and when we're considering or allowing our inputs to be functions themselves. So how do we compute a derivative of something like this? How would we use that chain rule? Well, what we can construct is something called a dependence diagram to help us sort that out. So we're going to draw one for this example now. A dependence diagram. So we start with our output, t. And now t is a function of two inputs. We'll call them x and y. And then x and y are both functions of an input we'll call t. Okay, so if our goal or desire is to find the derivative of t with respect to little t, then we want this derivative here, derivative of t, big T, with respect to little t. So how do we have to get there? Well, in order to get to t, we have to follow the connections that we have. So we have t going through x to little t, and then temperature going through y to little t. So for this derivative of temperature with respect to time, what we're going to have to compute are both of the ways, or we have to consider rather, both of the ways we can go from big T to little t. So the first way, I'll highlight here, going through x, we see that what comes out, or what is involved in that, is first taking that partial with respect to x, and then the derivative of x with respect to t. Notice again that there's only one input going into x, while there's two inputs going into t. So we take a partial of big T, but we can take a complete derivative with little x. All right, so we have those two components which fit in here. And then we have to take the other path as well to get to t. So we have t to y to little t. So what comes out there would be a partial with respect to y, and then the derivative of y with respect to t. So we just need to make sure we address all of those paths to get from our output to our input. So in that way, we're sort of unwrapping the function big T, because big T, you first have to do these x and y functions, and then one more layer up, then you have to plug in those to big T. Awesome. All right, great job going through this. So we have some more videos here that will give you some practice going through the examples and exercises. Thanks for watching. Keep up the hard work.